game. UMD XYZ 8601 8210 2651 0810 and 44. Okay, so the way to approach these games, the way I do it is to first look at the strategies that can't be dominated. And so it's like kind of like the things that you don't even have to worry about. So if player 2 plays strategy X, player 1's best response is U. So U is like, you can't be dominated. You're never going to find a combination of M and D that will dominate U. So U is safe from dominance, at least in the first round. And if player 2 plays Y, player 1's best response is to play M, because M gives the highest payoff to player 1, so M is safe. And then if player 2 plays Z, U is the best response. So if I was, going to try to find dominance in this game, I'd see, well, D is the only one that can be dominated. And now I look and I'm like, oh, wow, it is dominated. It's dominated by the pure strategy M, right? So M is always better than D no matter what. So I get rid of it, okay? And so now I essentially have a new game that, like it's as if D isn't even there, because under the common knowledge, wait, is this dominance or iterated dominance? This chapter,
Iterated
dominance, yeah. So under dominance, we're done with player 1, but under iterated dominance, U or M could potentially be iteratively dominated if something else is gone for player 2. Mm-hmm. But now I'm going to assume, since we're on iterated dominance, that player 2 doesn't. Player 2 knows that player 2 isn't going to play D, and we're going to take that into account when player 2 chooses their action. So now player 2 says, well, if player 1 plays U, I play X, so clearly that can't be dominated. If player 1 plays M, I play Y, so that can't be dominated. And before, Z was a best response to D, but it is D is no longer in play. And so Z is not a best response to either U or M. And so now we ask, okay, well, is Z dominated? And in this case, I mean, we could do the specific calculations, but here I recognize that a 50-50 mixture of Y and Z will dominate Z, or iteratively dominates. Okay, so if you mix X and Y, half of 6 and half of 1 gets you to 3.5, and that's better than the 2. And you mix 0 and 6, and it's a 3, and that's better than the 1. So this is one where I don't actually have to put the probabilities on X and Y and beat it, because there's sort of a more obvious one to deal with that. All right, so Z is iteratively dominated. And now at this point, if we look at U, U is for player 1, U is the best response to X, M is the best response to Y. So there is no more dominance for player 1. And for player 2, we already know that X is the best response for U, and Y is the best response for M. And so everything left is a best response to some strategy. And so nothing left can be dominated. So this, U, M, X, and Y, that set of strategy profiles that involve those things is the rationalizable set.
Okay, that makes sense. I wasn't doing it that way. I was like, I got the same answer, but I just wasn't sure how to know when to stop.
Yeah.
I saw D was dominated by U, and I saw that Z was dominated by a mixed strategy.
Mm-hmm.
But yeah, I just wanted to make sure I got the right answer.
At each stage, knowing when to stop is so we know the relationship for two-player games between dominance and the best response set, the undominated set and the best response set. They're the same thing in two-player games. So if something is a best response, it can't be dominated, and if something is not dominated, it's a best response to something. Mm-hmm. And so the first fact is the one that we use through this process in terms of identifying the things that can't be dominated. So you always, at least for me, I always look at the rows and columns for the game and ask like which ones are safe, like which ones can't be dominated, because it really focuses your attention on just a couple of things that might be dominatable. Right. And then once you find, you might find that nothing can be dominated. At that point, you're done. And then if you do find something's dominated, then you have to reevaluate the game as if you're starting, from scratch. Okay, now what's safe? Because maybe something that was safe before is no longer safe. But it's the exact same process. You take whatever part of the game is left over, judge which strategies are safe, which strategies are best responses to something from the other player, which means they can't be dominated, and then deal with the ones that aren't best responses. And you can either dominate them with a pure strategy, awesome, or you can dominate them with a mixed strategy, less awesome, take support, or you can find that they're not dominatable by a mixed strategy, which means they are a best response to something, and so you just leave them alone. And then they get a check mark.
Okay.
All right.
Thank you.
Okay.
Cool. So I'm good with that one. Does anyone else have any questions before I ask another one?
Go ahead.
Okay. Okay. So I didn't. Number 4. Will there be something like that on the test on question 7? I've never seen anything like that in my life.
Well, so I mean, it could be. So we actually Monday we solved this one in chapter 15. So we revisit this question in chapter 15, question 6 or 7. Basically looking at this game where it's no longer what's it called, a simultaneous move. So here we're assuming that the move is simultaneous, and in chapter 15 we take the exact same game and then say, well, suppose NBC has to go first, and then RBC goes, and then CBC goes. So we solved that one on Monday. But yeah, this could potentially be on. This would be a more challenging question because it's a little less conventional because it's got 3 players in it. But it's still not so crazy to figure out. So we can look at this one. So chapter 7.
If it's similar to the one on 15, I guess if Anita has the recording, she could send it to me if you want.
Well, it's not similar. I post the recordings on Blackboard now.
Oh, okay.
And I labeled them. I labeled the files by the questions that I cover, so okay. You'll be able to, so it's up there. This is so in chapter 15 we take the same game, but then we assume that the players move sequentially, which completely changes, and we're looking for the subgame perfect Nash Equilibria. So it's a completely different game as opposed to when everyone moves at the same time. So here we're looking for dominated strategies. So in this situation we're trying to see what strategies are never played by particular players, and so eliminate them, and then seeing if we can squeeze the rationalizable set down. Mm-hmm. So 8, 30, 27, 30, 16, 24, 13, 12, 50, and then the other side is 16. Oops. I should have made that bigger. 16, 24, 30, 30, 16, 24, 30, 23, 14, and 14, 24, 32. And this is, I'm just going to call them R and C. And then to get in this situation, player M makes a move, and his move is either 6 or 7. And then these guys have the same strategies. Okay. So we got to look for things that are dominated. So let's see. Is it always better for player M? And it doesn't matter where you start. So I'll start with player M, and I'll say, is one of those matrices always better for player M than the other? So what we have to do in that case, player M is the third player, so she has the third payoff. And I'm going to compare matrix to matrix, cell by cell, the third payoff, and see if one of them is always better than the other. So if I look at the left matrix, the first cell,
It's 7 and 7.
Well, the 6 and 6. When everybody plays 6, player M gets a 32 payoff, and if the other two players are 6 and she picks 7, she gets a payoff of 30 of 30. Okay. So if the other two players are playing 6, player M is better off playing 6. All right. If they go 6 and 7 and she plays 6, she gets a 27. Over here, she gets a 24. So 6 o'clock is still better. If in this cell she gets a 24, over here she gets a 14. So 6 is better. And over here she gets a 50. Over here she gets a 32, and 6 is better. So what did we just learn? Player M to play 7 is dominated, right? So regardless of the combination of choices of R and C, whether they play 6 and 6, 6 and 7, 7 and 6, or 7 and 7, player M's payoffs are always bigger when she plays 6 than when she plays 7. So 7 is dominated for player M, so it's eliminated from the game. So player M never plays 7, and under the common knowledge of rationality, both the other players know that. So no one ever thinks that they're in that matrix. They know they're always in the other matrix. Okay? And, so you could also do that by, you don't have to start with player 3. We could also do the same kind of calculations for like player R, for example, the player 1 position. We could say, if the other players are playing, 6 and 6, should I play 6 or 7? And so in that case, player R, like we're not assuming that we haven't eliminated M 7 for M yet. We could have said, well, if player M plays 6 and player C plays 6, then player R gets 14 by playing 6, and she gets 30 by playing 7. So she'd rather play 7 than 6, right? And if if the other two players play, if M plays 6 and C plays 7, 7 is still better for player R. And we go to the other side and we say, oh, if player 3 plays 7 and player 2 plays 6, player 1 still likes to play 7. And if player 3 plays 7 and player 2 plays 7, okay, well in this case, player 1 prefers 6/7. So in three of the combinations, player 1 would rather be in the 7 o'clock time slot.
Mhm.
But for some reason, if player C is in the 7 time slot and player M is also in the 7 o'clock time slot, player 1 actually prefers the 6 o'clock time slot. So in this case, player 1 did not have a dominated strategy, right? Anyway, so if we had started with player 1, we would have found that player 1 did not have a dominated strategy, and then we could move on to player 2 or player 3. I just happened to start with player 3. Player 3 is probably the easiest one to see visually, just in the way that you're comparing the cell to cell, matrix to matrix. It kind of is just an easier exercise. But anyway, we know player M does not play 7, and so we know we're never going to be over in that matrix. So now we can look at just the first matrix between R and C, knowing what player M is going to do. And so now we know that 6 is iteratively dominated for player R, right? Because 7 gives her, if player C plays 6, she gets the 30/14, and if C plays 7, she gets the 13/8, those yellow underlines. So we know that 7 dominates 6 iteratively for player R.
Right.
And now we move to player 2, player C, and we see that she prefers 6/7, knowing what's already been dominated for the other players. And so 7 for player 1, 6 for player 2, and 6 for player 3 is the rationalizable, it's the unique rationalizable strategy.
Okay.
So it looks like kind of overwhelming because it's got 3 players in it, and it looks, that means that it's like, different than what you're used to looking at. But the thought process that goes into solving it is not really any different than the thought process that goes into solving the game above. It's like looking for things that are safe and looking for things that are dominated, and then just iterating the process. But yeah, this is the solution that we did on Monday to the same game, but assuming that players move sequentially, that is the solution. Everything is quite different.
Professor, would it be 6,76 because MBC picks 6, or would it be 766?
So we know that player R plays 7, player C, which is player 2, plays 6, and player M plays 6. And I'm designating them in the order that we would typically, like R is player 1, C is player 2, and M is player 3. So I would put them in that order in the strategy profile. Does that make sense?
Yeah.
Because we did this problem a while ago, and I think the last time you wrote 676.
If I did, that's a mistake unless. So did we find the same cell as being rationalizable? I hope so.
We did.
Yeah. So then I probably just wrote them in the wrong order. But the order that it should be. So yeah, maybe I was thinking of player M as player 1.
Mm-hmm.
And
because player 1 first.
Right. And so then so that would, if I had designated player M as 1 and then player R as 2 and C as 3, then writing it 676 is correct. So it's like, it just really depends on, like, your map has to be clear what, like which strategy you're putting in which spot. So that's more of a presentation issue than a substantive issue. And I'm flexible with that on the exam.
Okay.
Yeah. If I had seen that you eliminated it down to a single cell and then wrote 676, I wouldn't take off for that because it's clear what you meant. So yeah, that's like a kind of minor thing. All right, other questions?
Can you go over, like, for quiz 3 and 4, can you do a similar question to that?
Quiz 3 and 4. So quiz 3 was a so I we can change the numbers. I mean, the numbers might not work pretty. I can keep the strategies the same. And we'll just throw random payoffs in here. Okay. So again, I have no idea. Yeah, this was just completely random playoffs. And let's see. Let's let theta minus 2 equal, we can keep the same beliefs as it was on the quiz. Okay, and so question 1 was, what's the expected utility of player 2's, of each of player 2's pure strategy? All right, and so the belief of player 2 about player 1 is theta minus 2. So player 2 believes that player 1 is going to play A 1/2 of the time and B and C 1/4 of the time each. Like that's what we mean by theta minus 2. And so the expected utility of player 2, the utility of X, given the utility of player 2, X given that particular belief, is equal to 2 times 1/2. So it's the payoff she gets by playing X and weighted by the probability of reaching X, plus 4 times 1/4, plus 1 times 1/4. All right, and that's equal to 2 1/4. And then the utility of player 2 of playing Y is equal to 3 times 1/2 plus 4 times 1/4 plus 2 times 1/4, which equals, let's see, it's 6/4 plus 4/4 plus 2/4, which equals 3. And the utility of Z is equal to 2 times 1/2 plus 0 times 1/4 plus 4 times 1/4, which equals 2. Okay? And so we could also, let's see,
Is
we
the
could,
sorry. Is it
uh-huh.
for like the first line? Is it 6 instead of 2?
Oh yeah.
Wait.
No, it's oh yeah, geez. It's not 6 instead of 2, but some of them are wrong. So I switched. I started with the right spot, so it should have been a 2, but then that
5
should have been,
and 3, right?
yeah,
Oh my
yeah.
god. I was like, what is? I thought I was doing something wrong. So
Oops.
we're looking at player 2's payoffs here, not player 1. Like
Yeah, we should be. And for some reason, I did the same thing on all the. So it's like I started the very first payoff in the right spot, and then my eyes switched over to the other side. All right. So it should have been 4, 1, 3, and 0, 6, 4. All right. Let's try this again. So that's going to be 4 plus 5 plus 3 over 4. Which is 12 over 4, which is 3. And then this one's going to be 8 plus 1 plus 3 over 4, which gives me 12 over 4, which is also 3. And this last one is 10 over 4, which is 2.5. Okay. And so if I asked what is the best response of player 2, given theta minus 2, we would say it is x and y, but not z, because the payoff for x and y and expectation are the biggest available. I think in the quiz, question number 3, I switched the BR1 to BR2 in class.
Yeah, you did.
Yeah, I thought so, because that was a typo when I wrote the exam, because you already basically did all the work for the best response, so I didn't want to like make you do the calculation all over again for player 2. So that would be the answer to question 3, given the change that we made. All right, is that clear? Sorry about the mistake. So yeah, it's you have to know what theta minus 2 and theta minus 1 mean, what sigma 1, what sigma 2 mean, and also not make mistakes as far as whose payoff is going. Make sure you're going down the rows correctly, the columns correctly, whose payoffs you're using. So if it's player 2, you should be looking at the second number, not the first. You should be looking at the columns, not the rows. And then we say, if sigma, question 2 was if sigma 1 is equal to a fourth, a half, and a fourth, what can we say about the beliefs of player 2 in comparison? Player 2's beliefs are incorrect. And specifically, you could say they're incorrect A and B are switched. So player 2 thinks that player 1 is going to play A, B, C, 1/2, 1/4, 1/4, when in fact sigma 1, player 1's mixed strategy is to play A, B, C, 1/4, 1/2, 1/4. So player 2 has the probabilities correct. She has the probability on C correct, but she switched the probabilities of A and B in her belief. So her beliefs are incorrect. And for the question, like the answer, I accepted player 2 is incorrect. Like that was full credit. But specifically, she's reversed the roles of A and B. Okay.
Yeah. So for question 2, what does that mean that the player is incorrect? Like, would you have to recalculate her payoff according
No,
to.
no. So theta minus 2 is player two's belief about 1. She thinks that player 1 is going to play A 1/2
Oh, got it. Yeah, I
and
missed.
quarter each. Yeah.
So this is saying, okay, I got it. So player 2 is believing something that player 1 is not actually going to do.
Correct. So
Okay.
this is kind of getting in anticipation of getting to equilibrium eventually, because in equilibrium it's always the case that sigma 1 is equal to theta minus 2 and sigma 2 is equal to theta minus 1. In equilibrium, you're always got to be correct in your beliefs, because if you're wrong, then you're not best responding, which means that you can't be in equilibrium. So you have to, so equilibrium requires correctness of beliefs.
Got it. Okay, thank you.
Okay. All right. And you said you had a question about quiz 4?
Yeah, can you do the same problem with different like numbers?
Sure. So here, the undominated set, the UD1 and UD2, that's just another way of saying, tell me the stuff that's not dominated, but not dealing with iterated dominance. So it's just finding the stuff that's not dominated for each player. And then what's the rationalizable set? So then apply iterated dominance, to the full game, and what's left over. And then what are the efficient strategies? So this one's this game would be hard, since it's a 4x4. This game is going to be hard for me to just put random numbers there, because it could turn out that I could get rid of everything by dominance, or it could turn out that nothing is dominated, in which case trying to find mixed strategies, mixed strategy dominance with 4 strategies is really, really hard. Like, it would take to show if all 4 are not dominated, but they're not best responses to pure strategies, it can take a long time to figure out how to prove that nothing else is dominated. Is there something in particular about this game itself that was like a step that was confusing?
I started doing the first question, and then I couldn't find UD2.
Okay, so maybe we can just do the same numbers, because I think if I randomize the numbers, it could end up, the chances of it ending up being a not useful example are fairly high. So these are numbers that so when I set up a quiz question like this, I basically start with like a couple of payoffs and then go back and forth, so that the game works out just so. So it probably takes me 20 to 30 minutes to write an example like this that does the things that I want it to do on the quiz. So like, it'd probably, if I throw random stuff in there, it's probably not going to work out very well. All right, so we had A, B, C, D, W, X, Y, Z, and let's see, 3, 2, 7, 1, 6, 1, 4, 3, 7, 2, 4, 0, 5, 3, 2, 4, 1, 5, 5, 6, 5, 7, 3, 3, 4, 3, 6, 7, 2, 4, and 3, 5. Okay, so and this kind of gets at like kind of where we started on one of the other questions. Like how do you start these things? I think the best thing to do is to find the stuff that can't be dominated first and check them safe. So if player 2 plays W, player 1 should play B in response, so B can't be dominated. So B, we already know for sure that B is in UD1. B is in the undominated set for player 1. If player 2 plays X, A is safe, so A is also in the undominated set. And that's all we're going to get, because A is the best response also for Y and for Z. Okay, so we know A and B are in the undominated set, but we're not sure about C and D yet. Next, we'll look for pure strategy dominance of either C or D. So if we can find something that dominates it by pure strategy, and it looks like we are, C is going to be dominated by A. So that doesn't take too much work. We get the 3 beating the 1, 7 beats 5, 6 beats 5, and 4 beats 3. So C is gone. So C is not in UD1. And now we have to look to see, is there a mixture of A and B that dominates D? All right. And so why are we picking A and B for dominance? Well, we know that A and B are both safe, so we're not going to try to dominate them. We're also not going to try to mix C in there because C is dominated. So A is always better than C. So it's not that a combination of B and C couldn't potentially beat D, but if B and C can beat D, then A and B can beat D. So there's no point in trying to mix with C. All right, so that determines why we're going to pick A and B as our strategies to try to dominate. So I'll let those probabilities be P and 1 minus P, and I'm going to see if there's a combination of A and B that beats D. So for that to be true, we would need to see that 3P plus 7 minus 7P would have to be greater than 4. Okay, that's the oh wait, oh no, yeah, good. That's fine. So if player 2 plays W, then player 1 would need to make sure that 3 times P plus 7 times 1 minus P is going to be greater than 4, so that the mixed strategy of A and B is going to be better than the payoff of D. So that gives us, we'll get I can subtract 4 from both sides. So we get 3 on this side, and then it's going to be greater than 4P on the other side. And then that means that P is going to be less than 3/4. So that's one of my conditions, that P has to be less than 3/4. A second condition is that 7P plus 4 minus 4P has to be greater than 6. That's our column X condition. And so I'm going to get a 2 over here, and I'll get a 3P over here. So P has to be greater than 2/3. And if we had a violation at this point, like if we had found that P has to be greater than 4/5, then we would stop, because we'd already know it's not possible. But here, because there still exists P's that live between 2/3 and 3/4, we have to go on. Like it's like we're still able to potentially dominate D. I don't have to do column Y, because any combination of 6 and 5 is going to beat the 2. So column Y doesn't add any extra restrictions. Column Y, A and B combination is always better than D, so we don't have to deal with it. And then column Z, I can already see that it's going to be P greater than 1/2. And that's because it's a 4 up here and a 2 here. So as long as I put, and if I put 50-50 on A and B, that would give me 3. And I need it to be greater than 3. So if I put just a little bit more weight on A, it'll be good. All right. And so those are the restrictions that I have on P in order for dominance. And so any P that's inside of the open interval 2/3 to 3/4 satisfies every column's condition, and so it dominates D. So there does exist a P that dominates D, and so D is eliminated. And that means that UD1 is equal to A and B. Any questions on that?
No.
No?
I have a
Yeah.
question. So
Uh-huh.
for, since 1/2 is less than 2/3, we wouldn't consider any P between 1/2 and 2/3 because it doesn't satisfy column.
Right. For it to be true, it has to A and B has to be better for every single column.
Okay.
And so P greater than 1/2 is a weaker condition than P greater than 2/3. So we just throw it away. It doesn't, like, anything that satisfies P greater than 2/3 will also satisfy P greater than 1/2.
Okay.
You only have to carry along your most aggressive greater than condition and your most aggressive less than condition.
Okay. Thank you.
Mm-hmm. Okay, and so now we got to look for player 2. And again, since this is UD2, we're not able to do iterated dominance yet. We have to look for across all of the columns to find UD2. So we can't take advantage of this common knowledge of rationality that player 2 knows that player 1 does not play C and D in order to find UD2. We're looking for the stuff that is just rational for player 2 for any set of beliefs. And so we go through the same exercise. If player 1 chooses A, the best response for player 2 is Z. So Z is safe. If player 1 plays B, player 2's best response is still Z. If player 1 plays C, player 2's best response is Y. And if player 1 plays D, player 2 plays X. That was a 7 down there, right? I think so. And so we've marked 3 strategies as safe. And so the only one we have to consider is W. Like, can W be beaten by a mixture of the other stuff? Okay. And let's see. Which ones are we going to try to dominate it with? Well, a combination of X, and this is a little tricky to think about because there's 3 of them to choose from, and they're all 3 best responses. I'm not going to pick Y and Z. Why wouldn't I pick Y and Z to try to dominate W? Any ideas?
Because any mixture would probably not dominate it.
Right. In the first row, if I mix between Y and X, the combination is always going to give me a 1. Whereas the payoff for W would be 2. And so a combination of X and Y can't dominate W. And so we either have to use X and Y. I'm sorry, we either have to use X and Z or Y and Z. I'm going to pick Y and Z to try to dominate W. And the reason I'm going to pick Y and Z instead of X and Z is that Z is always better than, let's see, wait.
It's always better except for when player 1 plays C.
Oh, sorry. Y is always at least as good as X, except in the last row, right? So I'm looking at Y and X, and I see in the first one they both have a 1. In the second row, Y is a 3 and X has a 0. In the third row, Y has a 7 and X has a 6. And in the fourth row, X is better. But if I'm mixing between Y and Z, Y is inferior to X, but 4 and 5 in the last row is always going to beat that 3 for W. So, like, basically in the last row, we don't have to worry about it. And so Y is always better than X, and we know we're not going to mix Y and X. So in the rows that matter, Y is going to be a better choice to try for dominance. So let's do Y and Z. So then I kind of repeat that again. So if I find a mixture of Y and Z that dominates W, fine, W's dominated, get rid of it. And the reason I'm picking y and z, well, I can't pick x and y together because they won't work in the first row. And y is better than x in every single row except the last one. And in that last one, the inferior y is still going to always dominate d because it's going to be mixed with z. And the mixture of 4 and 5 is going to beat the 3. And so we don't need the extra juice from that 7 from column x. So column x is the one that we want if we need extra in the last row, but we don't need the extra. So I'm going to look for a mixture of y and z that dominates w. So q, 1 minus q, and then I'm going to try to find a mixture that wins for every row. And I already see that mixture is definitely going to work no matter what q is for the last row. So I only have to worry about the first 3 conditions. And so for the first row, I'm going to need that q plus 3 minus 3q has to be greater than 2. And so that means 1 has to be greater than 2q. So q has to be greater than 1/2. That's the first row condition. The second row condition is that 3q plus 4 minus 4q has to be greater than 2, which means that 2 has to be greater than 1q. So again, oh wait. Oh, yeah, sorry. We didn't even need to do any algebra for the second row, right? In the second row, if I mix between y and z, I'm mixing between a 3 and a 4. That's always going to beat a 2. So that's not even, we're not going to have to do any, that's why I got q greater than 2, but well, we know q is always greater than 2. It has to, q greater than, yeah, q less than 2. It's always going to be satisfying. Whatever the condition was, now I don't remember what it was, but whatever the condition was, it was always going to be satisfied because any mixture in probabilities of 3 and 4 has to beat a 2. So there was no need to do any algebra there. And then the third row, we have 7q plus 3 minus 3q has to be greater than 5, which gives us that 2 on this side, 4q on this side. So here again, q has to be greater than 1/2. And the other side, I made a little algebra error here. That should have been q less than 1/2. Okay? And so here, there is no q that is both greater than 1/2 and less than 1/2. Okay? So W can't be dominated. Which means that W is a best response to something. And in particular, W will be a best response. Let's see. Oh, no, I can't. Let's see. W is a best response. Yeah, off the top of my head, I don't see it. But we know it's not dominated. We know that there's no combination of X, Y, or Z, or all 3 combined that would ever beat. Well, in fact, yeah. If player 1 was mixing between A and B 50-50, W would be a best response. You would not be able to beat W with a combination of X and Y, X and Z, or Y and Z. So W would be a best response in that case, I think. Anyway, but it's clear that W is not dominated. All right, so UD2 is going to be W, X, Y, Z. So everything's undominated for player 2. But now the final questions would be, okay, but apply iterated dominance. So even though nothing is dominated for player 2 knows that player 1 doesn't play C or D, right? So we see clearly that X is going to be dominated by Z iteratively. And we also see that W is iteratively dominated by Z, and Y is iteratively dominated by Z. So Z dominates everything once we know that C and D are out of the picture. Okay? And then once we know W, X, and Y are out of the picture, player 1 knows that. And so player 1, B is iteratively dominated by A. And so the rationalizable set is simply equal to the profile A, Z. Okay? Questions about that? All right. Other questions from quizzes or chapter questions?
Hi, Professor. This is
Hi.
Nan.
Hi, Nan.
So, I have a question about question number 7 in chapter 15.
Okay.
Only part C.
Question 7. All right, my screen got locked. Question 7, chapter 15. This looks complicated.
Yeah.
So 2-player game. Player 1 chooses I or O. If it ends, and so if player 1 chooses O, the game ends with payoffs X, comma 1. And then players play the Battle of the Sexes game, in which they simultaneously and independently choose between A and B. And so this is looks like this. And then A, B, A, B, A, B. And if they coordinate on A, it's 3-1. And if they coordinate on B, it's 1-3. And then presumably it's 0-0 otherwise. Okay. And then calculate the mixed strategy Nash Equilibria. And how does it depend on X? That's the one you're interested in.
Yeah, because there's so many cases. We need to discuss the range of X. Different ranges of X.
So let's see. Player 1 has 4 pure strategies. I, A, I, B, O, A, O, B. And in order for there to be, and so now we're not thinking about, so this game is a lot easier when we're only worried about the subgame perfect Nash Equilibrium, right? So we find the there's 3 equilibria of the battle of the sexes game, right? There's the AA, the BB, and a mixed strategy in between. One gets by playing O, and player 1 has to anticipate which of the 3 equilibria that they're in the battle of the sexes game, and then choose I or O accordingly, right? So subgame perfect in this game is pretty straightforward.
Yes.
But mixed strategy Nash equilibria of the full game, like the full set of mixed strategy equilibria, looks complicated. So let's see. These are the 4 pure strategies available. For player 1 to be willing to mix, she must be indifferent between the strategies she's mixing with, and those have to be best responses to what the other player is doing. Let's see. So player 2's job is to keep player 1 indifferent, but player 2 has to be also mixing. Has to be best responding to do so. Yeah, this is hard, but well, so the thing to do here is definitely to put this game into the matrix form. By the way, this is harder than you would get on your exam.
Okay.
You would not get this on your exam. So IA, IB, OA, OB, A, B for player 2, and the payoffs of out are always X and 1. And here we have 3, 1, 1, 3, and 0, 0. Is that right? Yeah.
Yes.
Okay. And so let's see. Any mixture that includes IB Let me think about this. So player 1 yeah. So it's not so there's a whole lot of mixed strategies that are kind of silly. So to write them all out, but like so first off, if player 2 plays pure strategy B, then player 1 is willing to mix if and only if X is equal to 1. And then there's a whole continuum of mixtures, right?
Mm-hmm.
You agree with that? So there's one set of mixed strategy equilibrium where player 2 plays B and player 1 plays any combination of IB, OA, and OB, provided that X is equal to 1. So that's one set of mixed strategy equilibria. Player 2 plays pure strategy B, X equals 1. Player 1 plays any combo of IB, OA, OB. Okay? So that's one set of mixed strategy equilibria. I don't want to write them down. It's tedious. And then similarly, there's another set of mixed strategy equilibria where player 2 only plays A, right? And in that case, of course, X has to equal 3. And then player 1 is willing to mix between IA, OA, and OB. So that's another whole set of mixed strategy equilibria, but it's only true when X is equal to 3. So we have one set of equilibria where player 2 plays B, another set of equilibria where player 2 plays A, and we know what those mixed strategy equilibria look like, but they only exist for one particular value of X. Okay? And so at most, one of those can exist. It can either exist for the B1 or for the A1, but they both can't simultaneously exist. All right? So the only interesting thing to investigate at this point is then a mixture of A and B. right? Well,
Mhm.
if player 2 is going to be indifferent between A and B, she would be indifferent between A and B provided that player 1 always chooses out, right? So if player 1 chooses out and player 2 chooses to mix between A and B, then and any mixture is okay, then player 1 is willing to choose out provided that the expected payoff of doing so, X, is bigger than the expected payoff of playing IA or IB under that mixture, right?
Yes.
And so it's going to depend on that mixture. But more generally, we can think about player 2 being willing to mix across player 1's full array of strategies, right? Because player 1, unless X is less than one, player 1's never going to play IB, right?
Yeah.
So let's see. So yeah. So yeah. You're right. There are a lot of cases. So there are 1, 2. I think there are like potentially 1,
1,
2,
2, 3.
3 interesting cases. One would be where because OA and OB give the same payoffs for both players, we'll just lump them together. So there's one set where OA, OB, and IA are played. There's another set where OA, OB, and IB are played. And then there's another set where all 4 are played by player 1. Okay? And so if OA, OB, and IA are played, but not IB, that creates a certain need for player 2, right? So the mixture of IA, OA, and OB has to be such that player 2 is indifferent to mixing between A and B, right?
Yeah.
Right? And in fact, that's not possible, is it? Because A is always going to be better for player 2 than B is, because you're mixing, in one case it's 3x and x, in the other case it's 0x and x, and it's the same for the other one. So if IA or IB are played in equilibrium, both have to be played. Okay. So so we don't have to worry about those. So in fact, we can worry about basically the full thing, where everything is played by player 1 and what's the response of player 2. Okay. And so, and the nice thing is that here we don't have to worry about the individual probability. We just have to worry about the sum of the probabilities for the third and fourth strategy, because they give the same payoffs for both players. So we could make this like RS and make this combination 1 minus R minus S, and whatever probability is assigned to 1 minus R minus S, we're like, well, any combination of O will impact the game because both players get the same payoffs there. So we can still solve it like we've been solving games all along. So it's like, in order for player 2 to be indifferent to this mixture of player 1, we need that 1 times R plus 0 times S plus 1 times 1 minus R minus S has to equal 0 times R plus 3 times S plus 1 minus R minus S, right? So that gives us 1 minus R plus R minus S has to equal 1 minus R plus 2s, right? And then the 1s are gone, and so we get 3s equals r, or s equals 1/3 r, whichever way we want to go. And so, then that's going to define this set of probabilities. So we need, let's see, player 1 playing r, 1/3 r, that's s, and then 1 minus r minus 1/3 r, 1 minus r minus 1/3 r, which is the same thing as 1 minus 4/3 r. And that's the sum of the last two probabilities. Sum of last two probs. Okay? So for a mixed strategy equilibrium, to keep, so player 1 is going to have to put that set of weights and you know, for player 2 to be willing to mix, and now player 1 has to be indifferent, of course, right? So we need to find the probability on B and A that will keep player 1 indifferent, right? Which is 3p plus 0. Wait, sorry, I'm losing my mind. For player 1 to be indifferent between all of these strategies. Yeah, sorry. For player 1 to be indifferent between all these strategies, we need that 3p plus 1 minus p equals 0p plus 1 minus p, and that also equals x. And so 3p, so we need 4p equal 1, so p equals 1/4, which means that x has to equal 3/4. So if x equals 3/4, player 1 and player 2 plays probability 1/4, 3/4. Player 1 is indifferent between all 4 strategies, and being indifferent, she's willing to mix. And if she mixes by the probability that we found over there, r 1/3 r, 1 minus 4/3 r, split between the other two, the final two, with appropriate restrictions on r, all right, to make sure that nothing is less than 0 or greater than 1. That will represent the full mixed strategy equilibria of the full game. There is no mixture of the first and the last two, or the second and you know, the 2, 3, and 4, right? And otherwise, we can look at the mixtures independently. So if player 1 is choosing just IA and IB, it has to be the case that in the mixed strategy equilibrium, that x is less than the expected payoff of that mixed strategy equilibrium, which should be 2. So as long as x is less than 2, then player 1 is willing to go in and play the mixed strategy equilibrium at the top, right? And then in order for player 1 to be willing to mix between the bottom two, yeah, x would have to be greater than 2, right? So there are a lot of cases, although a lot of the, it turns out that a lot of the cases aren't possible given the zeros that we get in the first row and the second row. But this question is definitely way harder than any question I would give you on the final.
Okay, because it's very easily to be messed up when like this.
Yeah, it's a messy problem. I mean, it's important. It's nice to be able to set it up like, okay, in order to solve for the set of all equilibria of this game, I'm definitely going to have to put this thing into the strategic form. And then I basically approach it like I approach any strategic form game, but there's a whole lot of cases. Some of those cases aren't mathematically feasible. Like I'm never going to mix between IB, OA, and OB. One, because, it's like the B is always going to, yeah. So it's like you just kind of have to work player one would mix between IB, OA, and OB. Player two would never be willing to mix between A and B in that situation. So some of the combinations, like there are many, fall out because of the way the payoffs arranged. But yeah, it's a tedious problem for sure.
But like the sub game of this question is really a good practice because it's easy.
The sub game of this one is a good practice, right? And so there should be there are 3 potential sub game equilibria, sub game perfect Nash equilibria, because there are 3 equilibria of the battle of the sexes sub game, and the one equilibria the Aaa equilibria of the sub game gives player 1 a payoff of 3. So whether she goes in or out depends on whether X is greater than or less than 3, right? Or if it's equal, then she mixes. She's willing to mix. And then the other subgame equilibria is BB, and then X, be the critical value of X is 1. And the third subgame perfect equilibria is with a mixture of A and B. It's got to be 50-50, which gives an expected payoff of 2 for player 1. And then the critical value of O is X equals 2. Right. So that finding the subgame perfect Nash equilibria of this game is definitely fair game for the test. But finding the full set of mixed strategy equilibria of the full game, that's beyond what I would expect you to do. It's too tedious. Not enough return for how tedious it is. What number was this? This was number 7?
Number 7 in chapter 15.
Cool. So at this point, through the office hours, we've done a lot of the practice problems from question 15 by now, and I'm posting videos, so yeah, that's good. All right, cool. All right, well, I've got to run to another to another class, any final last minute questions? Is that I'll do one more office hour on you guys. Your test is on Wednesday next week, right?
Right.
Yes.
So and we said maybe Monday. Yeah, I'll do one more Zoom session on Monday. Maybe probably the same time. But that way, anything else you work on, like between now and over the weekend, if you have any final questions, you can come on Monday. I'll post it on Blackboard, but yeah. So I'll do one more Zoom session on Monday.
Is it okay if we do F really quickly for this problem?
You do what?
Part F.
What is F? What are the mixed strategy subgame perfect equilibria of the game? So, part F, the MNE of Battle of the Sexes subgame is sigma 1 equal sigma 2 equal 1/2 1/2. So if player 2 mixes between A and B equally, like if she's playing A half the time and B half the time, then if player 1 plays A, she gets 3 half the time, and let's see, sorry. Oh, we can write out the payoffs, just so I was jumping to the conclusion, just for trying to speed through, but we can do this. So let's see, A B, player 1, player 2, AA for player 1 is 3 1 1 3 0 0 0 0. And so if for player one to be indifferent between A and B, given probability Q and 1 minus Q up here, her Q would need to be 3 times Q plus 0 times 1 minus Q is equal to 0 times Q plus 1 times 1 times 1 minus Q equals. Wow, that probably went too fast. We need that 3Q plus 0 times 1 minus Q equals 0Q plus 1 times 1 minus Q, which means that 3Q equals 1 minus Q, which means 4Q equals 1. Yeah, I was wrong about the probabilities. 4Q equals 1, so Q equals a fourth. So we need player, so that was wrong. So we need player 2 to play sigma 2 equal 1/4, 3/4 to keep player 1 willing to mix between A and B. And then player 1, the payoffs are the same for player 2 between B and A, but they're flipped. So player 1 to keep player 2 indifferent between the two is going to be 3/4, 1/4. All right. So to keep player 2 indifferent between A and B, she's going to have to play A 3/4 of the time and B 1/4 of the time. Otherwise, that encourages player 2 to play B more often because she likes B. Okay. So that's the mixture of the subgame. That's the mixed strategy equilibrium of the subgame. And the expected payoff of that mixture, so the utility to player 1 of sigma 1, sigma 2 is equal to, let's see. So if she plays A, she'll get 3 times 3/4. Oops, that's not true. 1/4. 3 times 1/4. And if she plays B, she gets 0 times. I'm sorry. If she plays A, she gets 3 1/4 of the time and 0 3/4 of the time. So the expected utility is just 3/4. The problem with the mixed strategy equilibrium is a lot of the time you're going to end up with zeros. And so the expected payoff isn't all that great. And so now that we know that player 1's expected payoff of entering the Battle of the Sexes game, if they're playing the mixed strategy equilibrium of that subgame, is 3/4, then in order for player 1 to actually be willing to go in, X would have to be less than 3/4. If X is greater than 3/4, player 1 would only play O. And if X is equal to exactly 3/4, player 1 is then willing to mix between going in and going out. So in that case, if X equals 3/4, player 1 is willing to mix between, is willing to put any probability on going in and out. So if X equals 3/4, then, and her in the Battle of the Sexes game, she was playing 3/4, 1/4, and so we could put, so she has to go in 3/4 of the time, 1/4 of the time, but we wait, but she can go into these. Again, she could do anything that adds up to P here, and then if that adds up to P here, she has to do the top, a total of 1 minus P. And so 3/4 of that 1 minus P she can do in that one, and 3 1/4 she can do in that one. Okay, but that's only if X equals 3/4. So if X equals 3/4, that solution looks more complicated than it really is. If X is equal to 3/4, If she goes in, she's got to play A 3/4 of the time and B 1/4 of the time, or she can go out, and she's indifferent to all that stuff. So she could go in 10% of the time, but when she goes in, 3/4 of that time, she plays A, and 1/4 she plays B, and she goes out 90% of the time. She could go out 10% of the time, and the 90% she goes in. She's 3/4, 1/4. Like any of those combinations is fine. But that's only if X equals 3/4. If X is less than 3/4, she's definitely going to go in and play the mixed strategy Equilibria, the subgame. And if X is greater than 3/4, she's definitely just going to play out, which is still a mixed strategy Equilibrium. She would play out. So like, for example, if X greater than 3/4, then player one is going to play out all the time. So never I. But when she goes out, A is 3/4 and B is 1/4. Right? So that's if X is greater than 3/4, and if X is less than 3/4, sigma 1 equals 3/4, 1/4, 0, 0. And of course, sigma 2 for all of these has to equal 1/4, 3/4. And so there's basically, for this question, there's 3 sets of Nash equilibria for the mixed strategy case. There's this for player one at 0, 0, 3/4, 1/4 if X is greater than 3/4, or it's 3/4, 1/4, 0, 0 if X is less than 3/4. And finally, if X is equal to 3/4, it's this here, which is complicated to write and say, but intuitively, it's like you can go in or out with any probability you like, but if you go in, you have to play 3/4, 1/4. And then you can subdivide what the probability on out is. You subdivide it any way you like on OA and OB. It doesn't matter. Okay. And then there's also other equilibria, of course, like not just this one with the mixed strategy in the battle of the sexes. There's also the Aaa Equilibrium and the BB Equilibrium. And then we go about the mixed strategies the same way. If in the Aaa Equilibrium, if X is greater than 3, then player one plays O, and for sure. And if X is less than 3, then player one goes in for sure. And if it's equal, player one can do any mixture of those things, in or out. All right.
Okay, thank you so much. I didn't know what to do after I got Q. I was stuck after I got Q.
Yeah. Nope. This is this is a complicated question, but it's worth thinking about for as far as the subgame perfect equilibria go.
Thank you
All
so
right.
much.
All right. Bye bye.
Thank you.
Thank you.